Yeah, so we saw instantaneous power developed by a force, or you can say delivered by a force. It is defined as rate of work done, where work done is defined as F dot ds. And of course, ds by dt is velocity. So power becomes also F dot v. Okay. So that is the instantaneous power delivered by a particular force. So now we can say that net power, that is the delivered by all forces, let's say F1, F2, n number of forces acting, that becomes summation of F dot v for all the forces, which can also be written as summation F whole things dot product with v, because obviously v is the common point, common velocity of the particle on which the forces are acting. So here velocity, this is the instantaneous velocity of the point of application of the force. So that's why this will become net force dot velocity. And further we had seen that this net power is also equal to rate of change of kinetic energy. Okay, so this is what we are discussing about in the last lecture. So now let's look at some simple application examples of this concept. For example, a particle of mass, suppose 5 kilograms, moves along the x-axis. So it is in 1D motion, such that x is equal to, let us say, this much as a function of time, where x is in meters and t is in seconds. Okay, so its x coordinate as a function of time is like this. So we want to find the net power due to forces on it at t equal to 1 second, and the net work done by all forces from t equal to 0 to t equal to 1 second. So this is a typical type of question which can be applicable for, it's relatively simple, so JEE Mains or NEET. Okay. And you can see there are a couple of ways in which you can approach this. So just try this question out, we'll discuss. Okay. So anybody figured out how we'll do the first part? Net power, how will you get from this information?
Or like find velocity and then find kinetic energy and then from that differentiation effect.
That is one very good option. That's correct. Because we are given x as a function, sorry, x as a function of time. So we can find instantaneous velocity as a function of time, right?
Yes, sir.
So from that we can find kinetic energy as a function of time, and we can find rate of change of kinetic energy. Any other option we have? So one option you have given, which is a feasible option, is we can make use of this, where kinetic energy is defined like this, and of course v over here is defined as dx by dt for 1D motion. So
Yes,
we can
sir.
make use of that. Okay. Now one more option is we can also use this definition, that net power is equal to the net force dot product with velocity. So in 1D motion, this net power will become what? It will become just product of these two, because both are parallel vectors, no? Velocity and net force, right? So net force will be mass into acceleration. So we can do this also, no? We can find acceleration. So this is another option we have, right? So try out by either of these two methods and tell me the answer quickly. With proper unit and everything. Very good, Rishita, correct.
Sir, I answered in the chat box.
Ethan, just check your answer once. Okay, so first of all, I'm just removing this extra terms which I've added here. Okay, now let's come to this question. So for instantaneous net power, one thing I can do is I can define, because x is given as this. So you can see instantaneous velocity is 4t plus 3t square. Okay. And therefore, I can even see instantaneous acceleration is 4 plus 6t. That information also, using the fact that. So now net power, I can either define it as rate of change of kinetic energy, okay, or I can also think of net power as net force into instantaneous velocity. So that becomes this. Okay. And the mass of the object was given to me as 5 kg. So if I go with this option, so at t equal to 1 second, I can see that the acceleration is 10. The instantaneous velocity is 7. The mass is 5 kg. Sorry, Ethan, your answer was correct, beta. Sorry, my mistake. Okay.
Yes,
so
sir.
the instantaneous power will become 350 watts. Okay. Or I can go with this option, that here this is differentiation of half m into 4t plus 3t square whole square. So this is a bit lengthy in comparison, but we can still do this. So it is half m into differentiation of this term. So this term's differentiation, when I square this, so 16 t square plus 9t to the power 6, right, plus 24 t to the power 4. Oh, just a minute, made a mistake here. this is t cube t square. Yeah, so this will become differentiation of 16t square plus 9t to the power 4, okay, plus 24 t cube. So it's half m into 32t plus 36t cube plus 24 into 3. That's how much? 72 t square. So this is the instantaneous power as a function of time. So now we'll just substitute t equal to 1 second in that. So this is requiring a bit more effort, but you can see we can calculate it this way also. Okay, now tell me, how will we find this second part? Net work done from 0 to 1 second. How will you calculate this? Ethan, have you worked this part out?
So the net work that I'm still doing, sir. But sir, I don't know if this is a long method or not. Sir, I was thinking integration of power, the net power.
That's
with
one way
respect
we
to
can
time.
do, because we know, but so we know that net power is mass into acceleration into velocity. So we can express this as a function of time and all that. And then work done we can calculate as integration of power with time. But if you really think about it, now this is doing extra work.
It's a law, yeah.
We also know that what is the net work done? It is the change in kinetic energy. No?
Oh yeah. Oh yes, sir.
So we can calculate the work done from 0 to 1 second as the final kinetic energy at t equal to 1 second minus the initial kinetic energy at t equal to 0. And this will be easier because we already found out v as a function of time, right?
Yes, sir.
Okay, so just quickly roll this up. Okay, so hope you all have worked out the second part. So you can see it's very easy to find the kinetic energy at t equal to 1 second. You already found out the velocity, right? Okay, so so 122.5 joules. This is what you should be getting as the work done, the net work done.
Yes, sir.
Okay. Okay, so this is one type of question which is very common to do with both power and calculation of work done and all this. That for a 1D motion, basically the kinematics is given to you. The displacement as a function of time or velocity of the as a function of time or whatever is given. Just a minute, people. I'll reshare the board. Okay, now the next type of question we'll look at is again something where we will have to relate the relationship between power and velocity and all that, and what we've learned in kinematics before, but not through a 1D motion, through a different situation. Now, in this example, we'll combine the concepts we've learned in projectile motion with this. So from the ground level, at time t equal to 0, suppose we are projecting an object of mass m at a velocity u like this at an angle theta. So the mass of the object this time is, let's say, 2 kgs. The initial speed is, let's say, 25 meters per second, and the angle is 37 degrees. G is 10 meters per second square. So you want to find out the instantaneous power delivered by the weight, that is the force mg, on this object at t equal to 1 second from projection at the highest point of the projectile motion, and once again at t equal to 2 seconds. If mass is given, initial velocity is given, g we have to take as 10 meters per second square. Now you have to use the formula for net power, sorry, the instantaneous power rather, delivered by a force. In this case, it will be the net power also, because mg is the net force acting during projectile motion. Anyhow, you have to use this, and for velocity at a given instant, you have to use the concepts from projectile motion. Okay, so this is another typical type of question. Okay, so I'm just working out the basic kinematics part of the projectile motion. You can continue working on the answer. You already started. So we take the vertical as our y-axis, horizontal as our x-axis, point of projection as the origin. You'll see an initial velocity u at an angle theta at time t equal to 0. Now, as this goes in this kind of a path, in general, at a time t, we have, so in this case, this will be 20 meters per second. This will be 15 meters per second at t equal to 0. And the acceleration, you know, is, okay, so horizontal component of acceleration is 0, vertical component of acceleration is minus 10 meters per second. So you can see that at some general time t, the horizontal component of velocity remains conserved. But the vertical component of velocity becomes like this. So this is the main thing now. So from this equation now we can figure out that at t equal to 1 second, first part that is, okay, Vx is 20, Vy is 5. So the velocity itself is 20 I cap plus 5j. And of course, the gravitational force acting on it is downwards like this. So the force we are talking about is this gravitational force. So the mass was 2 kgs this time. So it is minus 20 j cap in newtons. And this is the velocity in meters per second. So power delivered by gravitational force will be, gravitational force is dot product with velocity. So at this instant, you can see it will become minus 100 watts. And you can understand that power is negative because mg is causing a deceleration at t equal to 1 second. The projectile is on its way up, so it's decelerating. Okay, now anybody worked out the second and third part of this? Okay, so if you look at the overall projectile here, you'll see that for these numbers, u equal to 25 meters per second, theta equal to 37 degrees, g equal to 10 meters per second square, you'll get time of flight as 3 seconds. You will get range and all that doesn't matter, but as I said, horizontal component of velocity is 15 meters per second, and vertical component of velocity is, sorry, horizontal component is 20 and vertical is so 15 minus 10t, like this. So you'll also realize that as far as the overall projectile motion is concerned, it will reach the highest point exactly at half the time of flight, that is 1.5 seconds. And at the instant when it reaches that highest point, the velocity will be purely horizontal. The vertical component will be 0. Right? So that is an important property of projectile motion. So you see here that when it reaches the highest point, the time is exactly half the time of flight, and the velocity will be just u cos theta I cap at the highest point. And you'll see that here t is equal to 3 seconds. Therefore, it reaches the highest point at 1.5 seconds, and the velocity of the particle at that moment is horizontal at this point of time. So the power developed by mg will be how much? It will be 0, because mg is a vertical force now. So at that particular instant, there were 90-degree relationship. But for example, we had just seen that t equal to 1 second was a little before this, and at that time velocity was like this, whereas t equal to 1.5 seconds, so t equal to 2 seconds will be at a position like this. Now if we see at t equal to 1 second, the velocity was 20 I cap plus 5 j cap. Hence the power delivered by mg was minus 100 watts. But at t equal to 2 seconds, if you see, it's a symmetrical time, because 1.5 seconds or this thing, the half time is exactly the midpoint of these two times. So this will be minus 5 j cap. So the power delivered by mg at that time will become plus 100 watts. Because at t equal to 2 seconds, the velocity is on the way down. So that is why mg is delivering positive power. Because the kinetic energy is increasing. Whereas as we saw at t equal to 1 second, it was the other way around. The velocity was on the way up. So kinetic energy was decreasing. Okay, so this is another important aspect of projectile motion we can understand in terms of the power delivered by mg, which is in fact the net force. So that's the net power. We will hope this is clear to all of you.
Could you just show the questions once again?
Yeah.
Just one example.
So I'm just scrolling up to show you the question.
Okay, so could you just scroll back down once again?
Okay, so this actually contains all the three answers. Okay. This is the power delivered at the highest point. What happens at the highest point is that V becomes horizontal. Just at that instant, the instantaneous velocity is horizontal. So V is perpendicular to the gravitational force or energy. So power becomes zero. Whereas t equal to 1 second was before it reached the highest point. So it was negative power. T equal to 2 seconds is after it's reached crossed the highest point. So by now mg is delivering positive power because kinetic energy is again increasing. Okay, people, so done with this?
No, sir, 1 second.
Okay. Okay, done.
Sir, just in the 2 seconds. Just 1 second, sir. Yes, sir, done.
Okay. Okay, now one additional type of question we'll see, and we'll see two questions based on this, but the additional type is when we have a circular motion involved. Okay, so we'll start with this. So we have a particle which is in circular motion. So particle has a mass, let's say m, equal to 1 kg. It's in circular motion of a circle of radius r equal to something, let's say 5 meters. Okay. Now we have to find the power delivered by net force, or the net power, you can say, same thing. Acting on it. In the first case, if it is in uniform circular motion, with angular speed equal to 10 radians per second. Secondly, if it is in non-uniform circular motion, okay, starting from rest at t equal to 0 with a uniform alpha equal to 2 radians per second square. And third case, if it is in non-uniform circular motion again with speed varying with time like this. Speed in meters per second, t in seconds. Okay. So we are looking at a particle of given mass in circular motion of a given radius in 3 different situations. In one situation, is doing uniform circular motion with a given angular speed. In the second case, it's starting from rest in non-uniform circular motion with a uniform angular acceleration alpha of 2 radians per second square. And the third case, again, it's in a uniform circular motion, but this time the speed during the circular motion is given as a function of time as 20 minus 40. So in each case, we have to calculate the net power, or the power delivered by the net force. So this will also help us revise the concepts of circular motion, the 2 types of acceleration that you may or may not have remember about circular motion: tangential acceleration, centripetal acceleration, and those kind of things. Okay, people. So let's understand how this works out. So let's discuss about little bit about acceleration and force. Therefore, components of force in circular motion first. So if you look at a particle in circular motion, at some instant, let's say location of the particle is somewhere here. Means having angular velocity omega, angular acceleration alpha. So it's first of all, its instantaneous velocity will be in which direction? It will be in the tangential direction. So the velocity vector at any point of time in a circular motion is always pointing along the tangent to the circle at that point. Okay, so this is what we call the tangential axis, whereas this is called the radial axis. This is r cap and this is the tangential axis. So the instantaneous velocity is r omega theta cap, where theta cap is the tangential unit vector. And hence we have the relationship between speed and angular speed. V is equal to r omega, that kind of thing. Okay, now what about the acceleration? So in general, the acceleration will have two components, centripetal and tangential component. Centripetal component is responsible for turning the direction of velocity, whereas tangential is responsible for keeping the magnitude changing if that is happening. So generally, the acceleration vector, it consists of two components like this, the tangential component and the centripetal component. So this is minus r omega square r cap. So this is the net acceleration. So we can also see that the magnitude of centripetal acceleration is r omega square or v square by r. The magnitude of tangential acceleration is r alpha. Write it as capital R here. So the other ones as capital R. And that is also equal to rate of change of speed. Okay, so this is something important here, that tangential acceleration equals to rate of change of speed, whereas centripetal acceleration turns the direction of the velocity vector. Okay. So hence now if you look at net power, so net power delivered by the net force So one way to understand it is this. So if you see velocity vector and acceleration vector, you see that becomes like this, okay? Because r cap dot theta cap is 0. So velocity dot centripetal acceleration will be 0. And theta cap is 1. So velocity dot tangential acceleration will be Yes. Okay. So that's one way to understand it. Another way to understand net power is that it is equal to rate of change of kinetic energy. So it is m by 2 into differentiation of v square. So by chain rule, so this is chain rule applied to this term here. Now you can see that dv by dt by definition is tangential acceleration. So that's how we again get that net power is. Okay, so this is something very important to remember from the point of view of properties of circular motion. Okay, people, so clear about this?
Yes, sir.
Okay, so now let's come to this particular question. So the radius of the circular motion, so let's just go back to all the data that was given. So the mass of the particle doing circular motion, that was listed as 1 kg, the radius was 5 meters. In the first case, we had a uniform omega of 10 radians per second. So radius was 5 meters, mass of the particle was 1 kg. In the first part, we had a uniform circular motion at omega equal to whatever, 10 radians per second. So now you can see that omega is constant and alpha is 0. That is the definition of uniform circular motion. So speed v equal to r omega is also constant. But more importantly here, what happens is that the net power becomes 0, because alpha equals to 0 means tangential acceleration is equal to 0, which also means that rate of change of speed is 0. So that means kinetic energy is constant. So many different ways of understanding why the net power should be 0 in a uniform circular motion. Another way to understand what happens in uniform circular motion is that because the tangential acceleration is 0, the net force acting on a particle will be centripetal. F net will be mass into centripetal acceleration only, because tangential acceleration is 0 in UC. So the instantaneous velocity and the net force will be perpendicular to each other. Now, second part, we have taken initial angular speed to be 0. That is, it starts from rest at t equal to 0 with a uniform alpha of, what was it, 2 radians per second square. So this now means that the net power will be, you can write like this. So how we can write that as a function of time? Let's see. So from this and this, we can see that omega naught is 0 and alpha is constant. So omega as a function of time will become alpha t. So omega is 2t as a function of time. So v as a function of time is becoming r omega. So r was 5 meters. So v as a function of time is becoming 10t in meters per second. And also the tangential acceleration r alpha is 5 meters multiplied with 2 radians per second square. So that is 10 meters per second square. So we have a uniform tangential acceleration. So the power one kg mass into 10 meters per second square tangential acceleration into 10 t in meters per second instantaneous velocity. So it becomes 100 t in watts. Or you can also see this way, that alpha is equal to 2 meters, so 2 radians per second square. Radius is equal to 5 meters. That means tangential acceleration, which is r alpha, is 10 meters per second square, which means that rate of change of speed is 10 meters per second square and constant. So speed as a function of time will become 10t because initial speed was 0 at t equal to 0. So kinetic energy as a function of time will become 50t square. So net power as rate of change of kinetic energy. To do this also we get this. So that's another approach to the same thing.
Sir, for the P net, won't velocity also be 10t?
For the what, beta?
Sir, in that you've written 1 kg into 10 meter per second square like that.
Into 10
Oh no, wait,
t.
that's acceleration. Oh wait. Oh,
That is
that's,
tangential acceleration. Beta.
yes, sir, yeah, got it.
R alpha is the time. So earlier we saw the formula that we got when we take dot product of force with velocity, net force with velocity. It is mass into tangential acceleration into instantaneous velocity, right?
Yes, sir. Okay, got it, sir. I just did
Okay.
see that.
Okay, so written this part down.
Yes, sir. Done.
Okay, so I'm taking you to the third part of the question. Just try this out yourself. So same mass and radius of the circular path. Radius is 5 meters, mass is 1 kg. But now the particle is moving with a non-uniform speed of this 20 minus 4t as a function of time. Okay, work this out, anyone? So in this case, now you can see that there is a uniform tangential deceleration. In the third case, it's a circular motion with instantaneous speed as 20 minus 40. So this means that the tangential acceleration, which is rate of change of speed, is minus 4 meters per second square. It is in meters per second. So there is a tangential deceleration. Basically means that alpha is negative. So omega is decreasing with time, just as speed is decreasing with time. So tangential acceleration is negative, like that. Okay. So anyhow, so our instantaneous power, net power, again write as this. Okay, so it is 1 kg multiplied by 20 minus 14 meters per second multiplied with minus 4 in meters per second square. So it will be minus 4 into 20 minus 40. So minus 4, not 40. In watts. Okay, so now I want to do one more question which will involve application of work energy in a vertical circular motion situation also. You people have discussed vertical circular motion separately as part of circular motion.
Yes, sir. Circular VCM is done.
Okay, okay. So this will be a bit of revision of that also. Okay, so let's see this situation. Now we have a particle of mass, let's say 2 kgs, attached to a thread like this of length 5 meters. Now this is given an initial velocity at the bottommost position. Okay. Of let us say 30 meters per second. So first thing we want to do is, so G is like this, 10 meters per second square. So will the particle complete the vertical circular motion? Secondly, find the minimum and maximum tension in the thread during this motion. Third, find the power delivered by tension and delivered by mg when the thread is at 37 degrees with respect to the vertical. Okay, so the first part will give you a bit of revision of work energy, I mean of vertical circular motion, even the second part, and the third part of course we'll discuss in relation to power that we're discussing right now, power delivered by net force in case of circular motion.
So can you please show the third part of the last question?
Okay, people. So let's understand this question. So what is the answer to the first part? Will it complete vertical circular motion or not? What is the condition for completing vertical circular motion? Remember this formula, people? Yes, anyone? This formula is clear now?
Sir, if V naught is greater than or equal to root 5GL, then what does that mean? Or
It completes
string flat?
vertical circular motion, right?
Oh, okay.
ये पढ़ा था ना, याद है?
हाँ, but थोड़ा भूल गया था. I just forgot.
Okay. But you remember studying this now?
Yes, sir. Yes, sir. Now.
Okay.
I
So
just
what is the
thought
condition
of
for this now?
2GL and 5GL.
The tension is greater than equal to 0 at all points, है ना? In this case, so the string does not slacken, right? Okay, so now let's compare this now. So how much is our L? 5 meters here. So root 5GL is how much? Square root of 5 into 5 into 10. So that's square root of 250 or 5 root 10. That's approximately 5 into 3.2. So whatever. So we can see that V naught equal 30 is definitely greater than root 5GL. Okay. So the answer to this is that yes, it will complete vertical circular motion. Okay. So now once we know that it completes vertical circular motion, we'll also know that maximum tension is at lowest point, whereas minimum tension will be at highest point, right? When it is at this position, the speed is V naught. The tension in the string is T naught. You can see T naught is equal to mv square by L plus mg. And this will be the maximum tension. So we have M was 2 kgs. Okay. So this will become the maximum tension. Now, similarly, when it reaches the highest point, that is when the speed is minimum and also the tension is minimum. So let's say it reaches the highest point with a speed of V or V1 or whatever. And at that point of time, the tension is T1. Okay. So T1 here is the minimum tension, because T1 will become mg, or rather mv square by r, in this case mv1 square by L minus mg. So this will be the minimum tension. Okay. So now we can relate V1 and V by work energy. Okay. By conservation of energy, conservation of mechanical energy, we have half mv1 square is the initial kinetic energy minus the gain in potential energy, where this H will be equal to 2L in this case, because it's climbing from here to here. So vertical displacement or height of twice the length. So using this equation, we can see that V1 will be square root of V0 square minus 2G into 2L. So square root of V0 square minus 4GL. So let's work out that is how much. 30 square minus 4 into 10 into 5. So square root of 900 minus 200. So 10 root 7 will be the speed at the highest point. Okay. So accordingly, now the minimum tension is at the highest point, you can see. So therefore T1 will be 2 kg into minus 20. So 260 newtons. This will be the tension at the highest point. This is the minimum tension. So hope this is also clear. Now, for example, if we want to find at a point like this, basically what is happening, by the time it reaches theta, if the speed is v, you can see that for this point, by work energy, now the h you can see will be L minus L cos theta. So theta we have taken as 37 degrees. So 1 meter.
So
Yeah.
whatever this by conservation of energy that and uske aage whatever you written, that's the third part ke liye, no?
This
Because we
one,
already found
conservation of energy, say we found V1, right?
yes.
And from V1 we found out this tension. So this is the first part only, minimum tension. No?
Okay, okay.
So this minimum tension is coming out to be this much. This
So
value.
let's take the second method of doing it.
Huh?
That's like
Now
the
this
second
one?
method. No, like, yeah.
Yes. So
By
we are first
conservation.
finding V at this point, so that now we can find the power delivered by mg and tension.
Okay, yes, yes.
So you can see that tension is perpendicular to velocity. So power delivered will be 0, but mg is like this. So the angle that mg makes with velocity is 90 plus theta. So we'll use that for the power. But for that, we first need to find the velocity in magnitude. So at that point, V is becoming square root of 30 square minus 2 into 10 into 1, because h is 1 meter at that point. So it is square root of 900 minus 20, or V is square root of 880. So V will be something like this. So now you can see the power delivered by mg will be mg is dot product with velocity. Now at that instant, you can see velocity is like this and mg is like this. And this angle here, this one is 37. Okay, so it is mgv cos of this whole angle 90 plus theta. So it is minus mgv sine theta. So it is minus mgv into 3 by 5, where v is this value. So this is the power delivered by mg. Whereas the power delivered by tension will be 0. Because tension and velocity are perpendicular always. Tension acts in the centripetal direction in vertical circular motion, and velocity is tangential. Okay. So hope this is clear, people.
So then what is T1 over there? Just could you clarify that once again?
T1 is the tension at the highest point, but that is the minimum tension.
Achha, this is only minimum tension.
In a vertical circular motion, if you go back to your notes, you will see that the minimum tension is at the highest point, the maximum tension is at the lowest point, right?
Yes, sir.
So this maximum and minimum tension, we calculate it this way. T naught is the tension at the lowest point. It is mv square by L plus mg, where v is the initial velocity v naught. And at the highest point, the tension is T1, which is this centrifugal term mv1 square by L minus mg, which is the minimum tension. Okay. So that was a separate part. And here the power is a separate part because we are calculating the power delivered by mg neither at the lowest point nor at the highest point, but at this other in-between point where theta is 37, right?
Okay, so yeah, that's what I took. Right. Okay, thank you. Just 1 second.
Okay. So you complete writing this, and with this we complete today's session. Okay. I will send you the notes and the recording as soon as I can, probably by tonight then. Okay, people. So that's it for today's session. People, have a nice day.
So just 1 second. Could you just say that once again?
Other
Just,
notes. Yeah.
yes. So then what will be the final answer for power of mg? So